we're going to continue our look at conductors and electromagnetic fields. So let's start by remembering the condition for a good conductor, which is that the conductivity sigma should be very much greater than epsilon omega, where omega is the angular frequency of the field. You can also write that as sigma over epsilon omega is very much greater than 1. Under those circumstances, the dispersion relation simplifies and becomes k squared is equal to I mu sigma omega, in which case, of course, k is equal to the square root of I mu sigma omega, and using the fact that I is written as e to the I pi over 2, that is just given by root mu sigma omega e to the I pi over 4, or if you prefer, root of mu sigma omega over 2 into 1 plus I. And so if we're thinking about a complex wave vector k, we can write that as kr plus I ki, where the magnitudes of kr and ki are equal, and are both given by root of mu sigma omega over 2. Now if we substitute that into our plane wave and use Faraday's law as usual, then we come up with the following formula. We have that k crossed with E is equal to omega b. That's a fairly standard result that we've seen before, but now let's just think a little bit more about this. We're going to write k is equal to the magnitude of k multiplied by k hat, and that is just going to equal root of mu sigma omega e to the I pi over 4 times k hat, and therefore we have that the B field is equal to root of mu sigma over omega e to the I pi over 4 k hat crossed with E. So the direction is entirely as we would expect, but notice this extra phase difference, there's e to the I pi over 4, which has come about between the E field and the B field. And that's come about because of the complex wave vector, which in turn arises from the conductivity. So there is a phase difference between these two. Let's continue our examination of the standard plane wave form, and we're going to just substitute, and so we have E is equal to E0 e to the I k dot r minus omega t, which then is equal to E0 e to the minus ki dot r e to the I k r dot r minus omega t. And so here we have what's normally known as an attenuation, which means a distance-based reduction. You could think of it as a damping, though the word damping is generally used in terms of time variation, and in this case attenuation is a better word to use. Essentially, the magnitude, the amplitude of the electric field decays exponentially into the system. Whenever we have an exponential decay, we can characterize that, and so the characteristic length, that is the length over which the field will decrease by a factor of 1 over E, is given by delta is square root of 2 over mu sigma omega, and this is normally called the skin depth. Notice that the skin depth is a function of frequency, so it will change with the frequency of the EM radiation. So for copper, at 60 Hertz, which is the typical frequency of household electricity, delta is around about 8.5 millimeters. Up at 100 megahertz, which is higher in the frequency, delta is more like 7 micrometers, 7.1 micrometers. So it changes considerably. Notice also that this behaviour is completely different to the behaviour of evanescent waves that you get at the critical and beyond the critical angle in dielectrics. In evanescent waves there is no transmission, but in this situation there is transmission, though it is exponentially attenuated, and actually no energy is transmitted, what you can find is that the reflection coefficient is essentially equal to 1. So, what else can we think about in terms of conductors? The other thing we can think about is what we mean by a poor conductor. So a poor conductor would be a system which is like a dielectric, but has a small but non-zero conductivity. So there we would have k squared is equal to omega squared times mu epsilon into 1 plus I sigma over epsilon omega. And in this case, we know that that final term, the sigma over epsilon omega, is not going to be very large compared to 1. When we take a square root, we have that k is equal to omega times the square root of mu epsilon, and then we have 1 plus a half I sigma over epsilon omega. That's just using 1 plus delta to the n is approximately equal to 1 plus n delta. And when you multiply that out, you find that k is equal to omega times the square root of mu epsilon, that's the standard linear relation, plus I times a half root mu over epsilon sigma. And that final term, notice, is now frequency independent, and it will provide a small attenuation, though as sigma is small, it will not be particularly significant. And the main part of the behaviour is given by the standard linear relationship between the wave vector and the angular frequency, and of course square root of mu epsilon is 1 over c. Poor conductors are not something that we particularly study, but I thought it was interesting just to get that little bit of insight in there. So that's the end of these brief videos on conductors and EM waves. I will be providing some videos on plasmas, probably a couple of those, one on just plasmas themselves and the dispersion relation, and a further video just giving a little bit more insight.